Calculus, video 35, derivatives of exponents and logarithms. So here's what we know so far about the derivatives of exponents and logarithms. Really the only thing we know is the derivative of e to the x. We know that the derivative of e to the x is itself e to the x. We also know, though, that if we have some other function in the exponent there besides just x, right? So we're using u here as a function of x, that we need to use the chain rule. That the derivative of e to the u is e to the u times, chain rule says here, times du dx, or times u prime, if you will. All right, that's chain rule. Okay. For example, if we had the derivative of e to the 6x squared, right, where that u is like 6x squared here. The derivative is e to the 6x squared times the derivative of 6x squared, which is 12x. Okay, so that's really all we know so far about the derivatives of exponents and logarithms. And the reason why, if you remember, the derivative of e to the x was e to the x is in the graph of e to the x, we see that at any x value, here I have an x value of 2, the y value would be e to the power of 2. And the slope of the tangent line would also be e to the power of 2. The slope of the tangent line is the same as the y value. Which leads us to question, what if the base was not e? What if the base was 2, right? 2 to the x or 3 to the x? Would this stay the same? Would the y value and the slope of the tangent line be the same? Turns out it's not. However, what if the base is not e? What if the base is y equals 2 to the x instead of y equals e to the x? So it's not the same. However, if we picture y equals 2 to the x as opposed to y equals e to the x, honestly, when I'm drawing this, it's hard to tell which one I'm drawing, right? Y equals 2 to the x, y equals e to the x, y equals 3 to the x, unless we put some more points on there. Actually, let me back that up, because 2 to the x should be a little bit wider than e to the x. All right, it should grow a little bit slower than e to the x, since e is a larger base. If we plugged in a number here, let's say 3, we get a y value, that's 2 to the third, or 8. The question is, what is the slope of the tangent line? Is it also 8? Is it also 2 to the third? The answer is no. It's not, but it's close. It's close. In fact, if you go and kind of take a look at the two graphs, 2 to the x and e to the x, and if you were to map them together, they're very close to the same thing. E is that sort of perfect number where the y value and the slope of the tangent line are the same. When it's 2 to the x, or 3 to the x, or 4 to the x, or 1.5 to the x, it's the slope of the tangent line is almost the same as the y value, but not quite. In fact, it's off by a factor of a constant. We multiply it by the factor of a constant. Okay, so let's address that. Let's go through that. Let's see what is the derivative of 2 to the x, right? What is the slope of the tangent line for 2 to the x as opposed to like e to the x? Okay, before we can get here, let's do a little sidetracking. Let's remember back a little bit of algebra, some properties of exponents and logarithms. We'll need to use these properties of exponents and logarithms in order to answer this question, what is the derivative of 2 to the x? So let's just go back and remind ourselves, properties of exponents and logarithms. Properties of exponents and logarithms. Let's do exponents first. All right, so these are from algebra. We should remember them. If you don't remember these after I tell you, well, either way, you should write these down somewhere so you have them. But also, you need to go back and review and learn these properties of exponents and logarithms. We use them quite a bit. First one for exponents is if you take a base a, so it's a number, raised to the power of n, times that same base a raised to the power of m, you can add those exponents. That is a to the n plus m. And if you take, so that's property number 1. Property number 2, if you take a to the n divided by a to the m, you can subtract the exponents, a to the n minus m. Property number 3 for exponents, if you have 1 over a to the m, that is the same thing as a to the negative m. Or you could also write that like this. You could say if I have, I guess, a to the negative m, same way, just if you look at it from right to left here. If I have a to the negative m, that's the same thing as 1 over a to the m. Property number 4, I believe we're at. Any base to the 0 power is always equal to 1. We see that on all the graphs of our exponential functions up here. The graph at x equals 0 is crossing here at a y value of 1, right? Any sort of exponential base raised to the 0 power is 1. Other than, say, if that base is 0 or infinity, but we're talking about nice real numbers here, positive real numbers. And finally, if you have a raised to some power n, raised again to some power m, what can you do with those exponents? Hopefully you remember that you can multiply those exponents, a to the n times m, which is also equal to a to the m, this time, raised to the power of n, because multiplication is commutative, so n times m is the same thing as m times n, and so a to the n to the m is the same thing as a to the m to the n. All right, so those are our properties of exponents. Good to remember. Let's go properties of logarithms. And there are several more properties of logarithms than there are exponents. 1, if I take log base a of 1, that answer is always 0. If you remember, the logarithmic function is the inverse of the exponential function. So whereas the exponential function has a horizontal asymptote at y equals 0, it curves upward as we've seen here and passes through the point 1, 0. The logarithmic function is its inverse. And so instead of passing through the point, sorry, I said 1, 0. For exponential at 0, 1. For the logarithm, instead of passing through the point 0, 1, it's going to flip the x and y and pass through the point 1, 0. Instead of a horizontal asymptote at y equals 0, we will have a vertical asymptote at x equals 0 because it's an inverse function, and the logarithmic graph looks something like this. It's the inverse of the exponential function graph. So when you plug in an x value of 1, you always get a y value of 0. Log of any base a, where a is a number here, of 1 is equal to 0. That's our first property of logarithms. Property number 2. If you take log base a of 2 functions multiplied together. Picture m and n is not just numbers here, but 2 functions multiplied. You can separate those and make this log base a of m plus log base a of n. If 2 functions are multiplied inside of a logarithm, you can separate those as 2 different logarithms, both base a, where the 2 logarithms are being added to each other. Similarly, if you have a logarithm of m divided by n, you can make that the log base a of m, the numerator being positive here, minus the log base a of n, denominator having the negative logarithm. And just to expand this a little bit, this property is true for more than just 2 functions. For example, if we have log base a of m times p divided by q r, right, so 4 different functions, we can separate this into 4 different logarithms where the numerator functions are positive logarithms, so the m and p are positive logarithms, and the q and r get negative logarithms. All right, so positive log base a of m plus log base a of p minus log base a of q minus log base a of r. So anytime whatever function is in the numerator becomes a positive logarithm, whatever function is in the denominator becomes a negative logarithm. Okay, that was property number 4. Property number 5 for logarithms. If you have log base a of m raised to some power, so I'm going to use a lowercase n here to represent this as a number, not a function. Although I guess it could be a function. Typically we see this as a number here. What you can do is, this is equal to, that n is basically walking in front of the logarithm here, and you get n times log base a of m. This is one of the properties we're going to use here in just a minute to prove the derivative of 2 to the x. Okay, so we need to know this one. And this property here is just really a repeat of property number 2, where in m to the power of n, let's pretend n is 2 here, right? So like m squared. M squared is the same thing as m times m. And so you have 2 m's multiplied, which means you can separate them as 2 logarithms added. And since you have 2 logarithms added, it's 2 log base a of m's. If you want to kind of see what I'm saying there. If I have log base a of m squared, that's the same thing as log base a of m times m. And it doesn't have to be squared. It could be to the 4th power. You have 4 m's here, which is the same thing as log base a of m plus log base a of m, because you can separate this into 2 logarithms. And I have 2 of the exact same thing, therefore I have 2 log base a of m's. All right, it's like I'm bringing that exponent of m out to the front, but really I'm doing this process each time. All right, so that was kind of a proof, if you will, a short proof of the property above. Okay, let's see. We had property 1, 2, 3, 4, 5. Let's go property number 6. Log base a of that same number a raised to the power of x, log base a of a to the x, is equal to x. Okay, let's see about that. One thing you could do is since this is a to the x, you could bring that x out in front of the logarithm. That's right. So we could look at this as x log base a of a, and then I don't know why I'm doing this out of order here, but log base a of a is simply just 1. Let's think about how logarithms work. Log base a of a is equal to something. We know it's going to be equal to 1, but let's just box. A logarithm is the inverse of an exponential, meaning that if you take the base a here, raise it to the power of whatever it's equal to, in our case box, it has to equal to whatever is this inside part here, a. Well, a to what power is itself? That must be 1, therefore the answer must also be 1. Okay, so I apologize for doing this out of order. I should have said first, property here, log base a of a is equal to 1. Therefore, log base a of a to the x is equal to x times, you can bring that exponent x out in front of the logarithm, x times log base a of a, and since log base a of a is 1, you just get x times 1 or x. So maybe property here, log base a of a is 1, and log base a of a to the x is x. Okay. You could also view this as a composition of functions, where the outside function is log base a of something, and the inside function is like a to the x. And since it's a logarithm of an exponential, those are inverses of each other, and if you compose 2 inverse functions, you always get what you put in this case, x. Okay. Similarly, we have our last property here, a to the log base a of x. Again, this is an exponential function, a to some power, of log base a of x. That's a composition of a logarithm and an exponential of x, whose answer then, because if you compose a logarithm and an exponential, which are inverse functions, you always get what you put in. So we put in x, we also get out x. Okay, very good. We're going to use that last property again in our proof here in just a second. All right, so those are the properties of logarithms. You need to know those, so write those down somewhere. If you're not familiar with them, you need to study those. What I want to do is to take these last two properties and rewrite them in terms of base e. Right, so here I have base a, which could have been any of the numbers. Let's think about it in terms of base e. So remember that log base e of x? We use it so often, we gave it its own name. We call it the natural log, and we just write it like ln of x. But when we see ln of x, we know that means log base e of x. So when you see log base a of a to the x, that can write, if I'm thinking about e's, right, so base e here, I can think of this as the natural log, that's log base e, of e to the x. So base e of e to the x must also then equal x. Similarly, on the bottom one here, e to the power of the natural log of x must also equal x. All right, we are going to use that property there along with this exponential property that I mentioned above here. Right, that log base a of m to the n, you can bring that in out front. We're going to use that one. Both of those properties will help us prove the derivative of 2 to the x. Or maybe we'll go more general, and we'll go ahead and prove the derivative of a to the x. All right, so let's write those properties down. We'll kind of consolidate here. Here's what we know. We want to prove or find out what the derivative of some number a to the x is. We want to prove the derivative of a to the x. And let me just go ahead and tell you the answer is itself. So like 2 to the x, the derivative is 2 to the x. 4 to the x, the derivative is 4 to the x. Times, it's off by just a little bit of a factor, times the natural log of whatever base we have. And if it's base 2, this is times the natural log of 2. If it's base 3, it's times the natural log of 3. It's off by just a little bit from whatever the y value is. The derivative of a to the x is equal to itself a to the x times the natural log of a. That's what we want to prove. To do so, let's recall a couple of things, the properties we just had above. Recall e to the natural log of u is equal to u. Okay, that's this right up here. E to the natural log of x is equal to x. Although I'm not going to just use x here, I'm going to use some other function, namely a to the x. So if you're picturing e to the natural log of u, think about this as like e to the natural log of a to the x must be a to the x. Okay. The derivative of a to the x, well, let's rewrite this. Let's rewrite the derivative of a to the x. Instead of writing it as this form a to the x, let's write it as e to the natural log of a to the x. So the derivative of a to the x is the derivative of e to the natural log of a to the x. Right, those two things we've shown are the same. Now we know how to find the derivatives of xe, like base e exponents. Okay, but the first thing I'm going to do here is see how I have natural log of a to the x. Instead of a to the x, I'm going to take that x, I'm going to walk that out in front of the natural log using that properties of logarithms. So this is going to be the derivative of e to the x times the natural log of a. Or maybe we'll see this a little bit easier if we look at this as the derivative of e to, I'm going to switch the order here, the natural log of a times x. And it's important to note that the natural log of a is just a number, right? A is a number. The natural log of the number is also just a number. So the natural log of a here is a number times x. It's a coefficient of x. Now, what is the derivative of e to the u? The derivative of e to the u is e to the u times u prime. So recall, the derivative of e to the u, some function u here, is itself times u prime. That's the chain rule. Our u is some number, natural log of a times x. So the derivative of e to the natural log of a times x is itself e to the natural log of a times x times the derivative of the exponent, the derivative of u prime. When you take the derivative of x, that's just 1 times its coefficient, which is the natural log of a. And then we remember that e to the natural log of a times x is the same thing as e to the natural log of a to the x, which is the same thing as a to the x. So we go back and we replace this here with just a to the x, and we get a to the x times natural log of a. And we have proven it. So we have this. The derivative of exponentials. Right, we already knew what happened when it was base e, exponentials. When it was base e, the derivative is just e to the x, or if it's e to the u, it's itself e to the u times u prime. But if it's the derivative of a to the x, not just e, but 3 or 4 or 5 or something else, the derivative is itself still a to the x, but times the natural log of a. Or if you want to use some other function besides just x, what if it was a to the u? All right, so some number besides e, raised to the power of u, where u is some function of x. Then the answer here is a to the u itself times the natural log of a times u prime. All right, you still need the chain rule here if that u is something else besides just x, right? Picturing u as like 6x squared. We then would have to still multiply by the 12x, the derivative of u. So there you go. That is the derivatives of exponentials. That is what we want to know if our base is not just e. So let's just try a few out. I have 3 examples here that we can go through. Example 1, we'll start with maybe the easiest one here. Example, what if y is equal to 4 to the x? All right, so our base here is 4. What is the derivative? Again, feel free to pause it. Come back in a second when you're done. I have y prime is equal to, the derivative of any exponent is itself. So the derivative of 4 to the x, 4 to the x. But since 4 is not e, we had to multiply it by the natural log of 4. That's it. 4 to the x times the natural log of 4. Or some people like to write the coefficient. Natural log of 4 is a number. So some people like to write it as the natural log of 4 times 4 to the x. Either one. I kind of like this second way because we write our coefficients out front. We tend to. Very good. Let's try number 2. What if we have y equals, that's 1, 2, y equals 3 times 5 to the 2x squared. Now, when you're looking at this, that 3 is just a coefficient. It's just a number times 5 to the 2x squared. It's easier to see, I think, like here, like 3 times e to the 2x squared, which is, oh, that's just a number that's multiplied by e. But for some reason, when we have the 3 times 5, some students want to multiply those together and make that 15 to the 2x squared. This is not 15 to the 2x squared. That is not true. Please don't do that. You're just going to leave that 3 out there like it's a coefficient. Okay, so what is the derivative? If y equals 3 times 5 to the 2x squared, y prime is, again, pause video, see how you do. All right, 3 times, the 3 just hangs out. The derivative of 5x squared is itself. Don't forget that it is its own derivative. But because the exponent there is not just an x, right? Chain rule says times 4x, the derivative of 2x squared, 4x. But also, since the base 5 is not e, we have to multiply that by the natural log of 5. So, what do we have here? We have 3 times the natural log of 5 times 4. So maybe I'll multiply the 3 and the 4 together and call that 12. 12 times the natural log of 5 times 5 to the 2x squared. I lost an x, didn't I? Let me go back. Well, let's just do this. Times x. Probably I would have written it like this. Let's just make it right. 4 times 3, 12. Natural log of 5. X times 5 to the 2x squared. I like that the best. Okay, number 3. Last example here. What if our function is 4x squared, so 4x squared, that's a polynomial, times 3 to the sine of x. That's an exponential. And notice we have two functions multiplied together. So how do we find the derivative when we have two functions multiplied together? Product rule, right. Again, pause, try it yourself, come back. Okay, let's see. Y prime is equal to the derivative of the first one, that'd be 8x. And we're just going to leave 3 to the sine of x. That doesn't change. That's just our g function. Plus, we leave our 4x squared, and then take the derivative of 3 to the sine of x. The derivative of an exponential is always itself, 3 to the sine of x, times the derivative of sine of x is cosine of x, times, since 3 is not e, we have to multiply it by the natural log of 3. And we get something like this. We get 8x, 3 to the sine x, plus 4 natural log of 3, x squared, cosine of x, 3 to the sine x. And it looks like I can factor out, I have two terms here, right? I have this first term here, I have this second term here. I can factor out a 3 to the sine of x, and I can factor out a 4x out of this whole thing. So if I take out a 4x times 3 to the sine x, if I factor that out, I'm left with just a 2 in the first term, plus a natural log of 3 times x in the second term. There you go. So that is how we take the derivative of exponentials that are not base e. Right? The derivative of a to the x is a to the x times the natural log of a. The derivative of a to the u is a to the u times the natural log of a times u prime there if that exponent u is a function of x.